So I won't be talking about real stacks. The objects I will discuss have some similarities with stacks, but also some significant differences. My goal is to convince you of two things. First of all, that these Campana's objects lead to new and interesting classes of Diophantine problems, which I personally find quite appealing. But even if you don't think they're appealing, I mean, you have the right to disagree, then you should still care, because they're also very useful for the study of traditional Diophantine problems having to do with rational and integral points. So they pop up in the traditional picture of rational and integral points as well. So I'll first say some things about the case of curves, and then I'll go to higher dimension in the second half of the talk. So part one is going to be on Campana curves. I should really be saying Campana curves, but it's difficult in English to throw in this one French pronunciation. So, and I learned about these things and their arithmetic via slides, which I found on Bjorn's website. So he has a very nice set of slides called the projective line minus 3 fractional points, which at some point got me interested in these problems, and I encourage you to look at these. So a definition. So a Campana curve is simply, say, over some field K, is a pair consisting of a curve C and a Q divisor D. So C is a smooth and projective curve. And D will be a Q divisor on C, but not just any type of Q divisor. So D will be of a specific shape. So D will be of the form sum of epsilon I di, so a finite sum of prime divisors di. And the coefficients, epsilon I, they will belong to a distinguished set of rational numbers. So this set will be this set of all numbers of the form 1 minus 1 over m, where m is some integer at least 2, or, well, we're also adding the number 1. I should... we will formally write epsilon I equal 1 minus 1 over mi, where we use the convention that 1 over infinity is 0. So we allow mi to be infinity. Okay, so these are Campana curves. There's nothing more to be said on these objects. Well, so then let's define what Campana calls Orbifold rational points. They're not quite rational points. They're somewhere in between rational and integral. So I'll call them Campana points. So let's fix a model, curly C, curly D, of the pair CD over OKS. So, okay, I'm assuming K is a number field, otherwise. So I'm fixing a model over OKS, where S is some finite set of primes. And I'm assuming that by choosing S large enough, I can assume that this is what I call a smooth model, by which I mean so C is smooth over spec of OKS. And curly D will be eta. Right? So I'm working over some suitable localization of the ring of integers. And I have some relative curve over this ring. And then I have some horizontal divisors, di. And of course, I've made sure that these divisors are étale over the base. So I've deleted all points here on the base where they ramify or where maybe two components intersect and so on. So this is really a very nice picture. And I'll write C0 for the support, well, for the complement of the support of D. So by the roundup of D, I write the roundup for the support of D because it's convenient notation in this case. So let's define the set of Campana points, OKS points on this model. So my notion of Campana points will depend on the choice of model and the choice of S. So this will be the set of points. So K points in C0 with the following property. So any such K point will extend to an OKS point, curly P, from on C, right? So you'll get an induced section for this structure morphism. And I want this extension to have the following property. So whenever curly P, or rather its image, meets curly DI above some prime V, not an S, then the multiplicity of intersection is sufficiently high. So the local intersection multiplicity is high enough, and high enough, well, what does that mean? It means at least the number mi, which I put here in the definition of the Campana curve, right? So I have this Q divisor with coefficients, and the higher these coefficients are, the closer they are to 1, the higher I want my intersection multiplicity here to be. So you should think of, well, this is maybe, so I have some section, curly P, and whenever it intersects above some place V, not an S, then I want the local intersection multiplicity to be at least this number mi. It could be anything. So it's either 0 or at least mi above every prime, not an S. Of course, if my mi is infinity, then I'm not allowed to intersect at all above places not an S. So then this means that with respect to this one component at the boundary, I really want to be an integral point rather than just this approximation to, well, whatever. Okay, so this looks like a weird definition maybe, but it's a way to interpolate between classical rational and integral points. Obviously, because if I choose my boundary to be empty, then I recover the classical notion of rational points. If I choose my boundary to be, let's say, purely logarithmic, so if I choose all my coefficients equal to 1, then I recover the classical notion of a ds integral point. And in general, I have an intermediate class of points lying somewhere in between rational and integral. And that's the class of points we're going to look at. And if you're still wondering why this is useful, then I understand, but this will come later. So for now, let's just ask, without, going into motivation, this will come later, let's just ask questions about properties of these sets C, D, okay, S. Okay. So the classical cases of rational and integral points suggest that one should look at the so-called Orbifold canonical divisor. So this is KC plus D. And in particular at its degree. So let's call this chi. It's 2 minus 2 times the genus of C plus sum of all epsilon I times degree pi. Okay, so this is a number, a rational number, which should govern to a large extent the arithmetic of these, the properties of these sets CD, OKS. So the obvious questions are, if chi is positive, then we're talking about a Fano object, so you should expect to see many of these points. And so you're interested in counting how many of them there are. If chi is equal to 0, then you're in this somewhat intermediate case like, let's say, Calabiar or elliptic curve or whatever. Something approximating an elliptic curve. So you should expect to see some points, but maybe not as many as in the Fano case. And if chi is negative, then you're in the general type range. So you should expect to see only finitely many of these points. So maybe it's good to look at an instructive example. So let's take C to be the projective line. Let's take D to be a divisor supported at 0, 1, and infinity. So I let D be equal to 1 minus 1 over sum m naught times the prime divisor 0. And then, yes?
Is this minus the sum?
Yes, it's going to be.
This is the negative.
Yes.
Of KC plus.
Yes, this is good. Sorry, yeah. So I choose an orbifold boundary supported at 3 points, so 0, 1, and infinity. And I wonder what my sets of orbifold or Campana points actually look like in this case. So, okay, so let's look at an integral point on P1. So an integral point can be written x over z, where x and z are coprime integers. So imposing this tangency condition, which I just introduced, with respect to the divisor supported at 0, means that whenever my x reduces mod p to 0, then the multiplicity of intersection should be at least m naught. So the valuation of x should be at least m naught with respect to such a prime. So this means that x should be what some people call m naught full. So this means that the radical of x to the power m naught divides x. Okay, and then similarly for z. So you get a similar condition for z. So z should be m infinity full. So whenever a prime divides z, then that prime to the power m infinity should divide z. Okay, and then then we have to figure out what the condition with respect to the divisor supported the components 1 means. So then let's say that y is equal to z minus x, or x minus z, whatever. So then we see from the same description that our y should be M1 full. Okay, so our set of Campana points, I'm having a really hard time with these buttons. Okay, so what is in this case our set of Campana points? So we're talking about the set of primitive integral triples for which x plus y is equal to z, x is m0 full, y is m1 full. Say again?
I think maybe you'd want y equals b minus x.
Yeah, I think so, yes. Doesn't really matter, but okay. And z should be m infinity full. So this is a concrete set of, I mean, this is, for me, this is an appealing Diophantine problem to understand the properties of such a set. So let's look at the case where all mi's are equal to 2. So then we're talking about squareful triples. So triples of integers satisfying this additive relation for which all exponents in the prime factorization are at least 2. Okay, and calculating chi yields 1/2, which is positive. So we're talking about some Fano curve in Campana's sense. So we should expect to see many rational or many Campana points. So the question is, can we actually count them? So let's look at the set of such squareful triples. Where some naive height of the triple is bounded by some number b. Can we understand the asymptotics of this counting function if v goes to infinity? And heuristics suggest that one should see roughly b square root of b as the growth function for this counting problem. And it seems like an innocent problem, but it's incredibly difficult. So I think analytic number theorists have tried hard and haven't really come close to solving this kind of problem. So the best known results are by Tim Browning and Karel van Valkenborg. So they proved that this counting function grows at least as c times 1 plus something going to 0 times the square root of b for some constant c, which they calculated, they approximated it numerically. It's something ugly. And they could also prove an upper bound of the form b to the power 3/5 plus some epsilon. So somehow they were able to get very rough, a very rough sandwich for this counting function, but it seems to be a very difficult problem to actually get asymptotics for this counting problem. So then if all multiplicities at the boundary, so m0, m1, and m infinity are equal to 3, then we're talking about cubeful triples. And our order characteristic is equal to 0. So then the question is, what should we expect? So should we expect maybe, by analogy with elliptic curve, should we expect maybe after taking an extension, something like some power of log b for the growth function of this number of Campana points. So there is a little bit of evidence in this direction by someone called Abderrahman Nitash, who proved that the growth is indeed at least logarithmic. And then there is the opposite case. So when we go to the general type range, so this happens whenever 1 over m0 plus 1 over m1 plus 1 over m infinity is smaller than 1. So then we're in the general type range. Then the natural question is, does the Orbifold analog of Mordell's conjecture hold? In particular, can we then prove that these sets of x, y, and z satisfying these constraints, that these are finite sets for such choices of m0, m1, and m infinity? So I think it's an observation which is due to, I think, polyotélène. That's because that's what Campana seems to write in his paper, that the ABC conjecture, in fact, implies Orbifold Mordell for the case which the example that we just looked at, so P1 and 3 points at infinity. So this is, one can deduce from the ABC conjecture that these sets are finite. And in fact, one can deduce a bit more. So let CD be a Campana curve over a number fields K, which is of general type. So by which I mean that KC plus D, so the Orbifold canonical divisor is a big divisor. Then the ABC conjecture implies that our sets of Orbifolds or Campana points are all finite. But I don't know a single example of this kind of Campana problem, so a single curve of this type. At least if we keep the mi's away from infinity, because that's a different case. But I don't know a single example where we can prove this kind of result unconditionally. So this seems to be a very, very difficult problem. I'm not sure how much easier it is than proving the ABC conjecture, really. But anyway, good. So hopefully this gives you some. Okay, so this is, I guess, due to Abramovich, but I've written down the details somewhere myself. So okay, so now 2 questions remain. So, well, first of all, we don't really seem to be able to prove anything on these sets. So, well, isn't that a problem? And secondly, why would we be interested at all in these sets? So why should we be interested? So the slogan is that Campana points, they control the behavior of rational points in fibrations in certain cases. So classical rational points. So let's formalize this as follows. So let K be a number field. Let X be a smooth projective variety over K. And let C be a curve over K. And assume that pi from X to C is a nice fibration. So a fibration with a smooth, geometrically integral generic fiber, let's say. So whenever we're given such a fibration, we can attach to pi something called the orbifold base of the fibration. So it's something introduced by Campana. So how does this thing look like? So this means that we have to equip C with a Q divisor, which will turn C into a Campana curve. So what is this Q divisor? So maybe I should make a picture. So we have some X over C, and of course, most fibers most fibers will be smooth, but there will be singular fibers, and some of these singular fibers will be very specific. So they will have the property that no irreducible component of the fiber has multiplicity 1. So all irreducible components have multiplicity at least 2. So, so whenever this happens above some point P, so whenever P is a closed point of C such that the fiber of pi over P does not have an irreducible component of multiplicity 1, then we say that the fiber over P is a Campana multiple fiber. This is different from being a classical multiple fiber, because being a classical multiple fiber means that that the whole fiber as a divisor is divisible by some integer at least 2, whereas in this case, it could very well be the case that some components have multiplicity 2 and others have multiplicity 3, and that there is no single integer dividing the whole fiber as a divisor. So this is blackboard number 1. Stop. Yeah. So then, what is our divisor d pi? So I take the sum over all p. All points of the base such that the fiber is a Campana multiple fiber. And I assign weights to these points. So I say, well, I put the coefficient 1 minus 1 over MP in front, where MP is the minimal multiplicity of a component in my fiber. Right? Okay, so this divisor d pi keeps track of what the minimal multiplicity of components in these fibers of the fibration are. Okay. So now the key point is going to be the following. The key point is going to be the following. So we have our fibration pi, we have our divisor d pi on the curve, on the base curve. So let's take a model query C, query d pi for C d pi over some localization of the ring of integers. Then enlarging S if needed we have the following. So the rational points on X map down to Campana points on the base, right? So this tells you that there's rational points on the total space are constrained in a way governed by the geometry of this pair C d pi, right? So understanding the arithmetic of these sets tells you something about where the rational points in the fibration can actually live. Of course, if you have a fibration where all fibers have multiplicity 1 components, then this orbifold-based object is just going to be the trivial object C, so you don't really get any new information. So this is really only useful if you're dealing with fibrations with multiple fibers in Campana's sense, or in the classical sense. But these are interesting objects, and so this allows you to, in some cases, prove new Diophantine results by exploiting what you know on Campana points. But then the question was, do we know anything at all about these Campana points? Because I haven't stated a single positive, interesting result on Campana points yet. So maybe this is all, well. OK, so let me give one example of a statement we can actually prove about these points. So instead of working over number fields, where things are very difficult, I'll work over function fields, where things are still difficult, but maybe a bit less so. So let's K0 be a field of constants. Let B be a curve over K0, and let K be the function field of this curve. So the definitions I've given of Campana points over number fields, you can also give them over function fields. You can do the same thing. So given a Campana curve CD over K, you can build a model curly C, curly D over B. And then for suitable open subsets U of B, well, then we're interested in the properties of the sets of sections over U of the morphism down to B. So we're interested in rational sections of this structure morphism, right? So this is the same picture as before. So we have a base curve and some nice model, and then maybe away from finally many primes where we have, say, bed reduction. We're interested in these sections which behave nicely, sections of the structure morphism, which behave nicely with respect to the given sections, giving the Orbifold structure. So we're interested in understanding how these sets of sections actually behave. So I should again switch whiteboards. Sorry for that. So Mordell's conjecture was known over function fields for a long time, before it was proven over number fields by Faltings. I'll be discussing the analog of Mordell's conjecture over function fields for these orbifold pairs, for these Campana pairs. So a typical hypothesis you meet when working over function fields is that, if CD is a pair as I think I'll bring this down a little bit because this is annoying. So if CD is a Campana curve as before, well, then you cannot hope for, say, finiteness of the set of Campana points. if you don't impose at least that the pair is non-isotrivial. So we say that CD is isotrivial if there exists a pair C0 D0 over K0 such that the base change of CD to the algebraic closure of K is isomorphic to the base change of C0 D0 tensor product over K0 algebraic closure of K. Okay. So, and this is a typical assumption you see in function field arithmetic. If you have an isotrivial family, then you'll get many points, which is something you don't want to see in Mordell's theorem. So we need at least this kind of assumption. But here something interesting will happen. So this is a point where the arithmetic of these Campana points deviates from what we typically see in function field arithmetic. So there exists non-isotrivial Campana curves of general types over function fields which do have infinitely many points. So I can give an example. So let K not be Fp. Let K be Fp bracket C. Let C be P1 over K. Assume that P is at least 5. And let D be the divisor 2/3 times 0 plus 1 plus infinity plus T to the P. Okay, this is a slightly sloppy notation, but this is so next to the 3 horizontal divisors I was considering already in the examples, I'm adding a fourth one. So this is a pair which is of general type. Because the order characteristic is equal to minus 2/3. It's not isotrivial. Of course, it would have been isotrivial had we not included the last point, but we did, and this makes it non-isotrivial. But still, if you look at sets of Campana points for this pair, then you will find infinitely many of these. Basically because all points on P1 with coordinates in the field K to the power P, so the field of Kth powers in P, all of these points they will also be Campana points, because if you have 2 of these, well, if you have a Pth power, how should I say? So the picture is I have horizontal divisors at 0, 1, and infinity. And then I have this point, which is a bit hard to draw, because if I take the derivative, it's going to be 0. So it's everywhere horizontal, but it is not globally horizontal. So it's a bit, well, it's locally horizontal, but not globally. And whenever I throw in another of these sections, which is a Pth power, then I get the same picture. So it's everywhere locally horizontal, but not globally. So whenever I intersect such a section coming from K to the P with a horizontal or locally horizontal section, then I'll get a high intersection multiplicity.
Is it explained because it is these in the limit of Frobenius?
Yes, yes. Yeah, so you need, okay, so the point I'm trying to make is that non-isotriviality is no longer good enough for these Campana curves. If you want to prove a Mordell theorem over function fields, you need something stronger. So I can now state, I guess, a theorem of my own, well, with others. So the right statement would involve the language of the Kodaira-Spencer map, but I'll state a simplified version. So this is a theorem by Stefan Kebekus, Georges Pereira, and myself, which says the following. So let's K be as before, so a function field. let CD be a Campana curve of general type. So rather than discussing the Kodaira-Spencer map, I will subdivide into cases. So if the characteristic of K is equal to 0, then assume that the pair CD, or rather C and the support of D, is not isotrivial. So in characteristic 0, this is good enough. If the characteristic of K is positive, then assume that the affine curve C0, so this is the complement of the support of the boundary, assume that this is not defined over the smaller field K to the P. Right? Then under these assumptions, my set of, so once I fix a suitable model, which I always have to do, and once I fix a set of primes, but once I've done that, my set of Campana points on this Campana curve is finite. So this is really I think the optimal version of the analog of function field Mordell and function field Siegel as well, because it also includes Siegel. For these Campana curves. So this is really a generalization of the whole spectrum. So you have rational points, integral points, but also everything lying in between and all kinds of mixed forms of these points. So this is nice. I think I hope people like the statement by itself, but I think it also has some nice applications. Well, so no, I mean, you can just assume K0 to be algebraically closed, because if you can prove finiteness after going to the algebraic closure, then you also already had finiteness before that.
But the condition about not being defined as K.
No, so this is a condition which doesn't have anything to do with well, okay. You can assume in the statement that K0 is algebraically closed, but that implies it for any K0, I think. No?
The function field over the algebraic closure, the p powers in that contain all the p powers in the original field.
Exactly.
So it's defined by the p powers in the original. No, that doesn't work. Okay, here. Okay. I don't know.
Well, okay, so assume, so in the paper we write K not to be, I mean, we assume K not to be algebraically closed, but it shouldn't depend on this.
It seems that the hypothesis that it's not defined over
Yes.
P
Yes.
becomes stronger.
Okay. So this is, as I said, this is not the actual hypothesis in the paper. We have a Kodaira-Spencer map hypothesis, which is not exactly this. I simplified the statement a bit for this talk. Good. So and as I tried to explain, this has applications. So for example, well, I explained how Campana points control the behavior of rational points in fibrations. So some very good classical geometers, they've constructed fibrations. This was in characteristic 0, so we had to redo their work in characteristic P, but they've constructed fibrations, genus 2 fibrations on surfaces such that the orbifold base attached to the fibration is general type. Right? So this is work by, for example, Campana himself, but also by Lydia Stopino. So they've constructed such fibrations on surfaces, genus 2 fibrations with this property, and with the property that X is simply connected. So having multiple fibers is in a way is orthogonal to being simply connected. So it's very hard to have both multiple fibers and for such a fibration and to have simply connected total space. So somehow these are very delicate constructions. And what we were able to do using our theorem is well, so we transported this to global function fields. So we found simply connected surfaces over global functions fields such that the set of general type, right? So we found general type simply connected surfaces for which we could prove that the set of rational points is non-Zariski dense simply by taking such a construction, making sure that our orbifold Mordell theorem applies. So then we know that rational points will have to lie infinitely many fibers of pi, because we know that the set of orbifolds or Campana points on the base is finite. So and rational points map down to the Campana points on the base. So you know that rational points will have to lie infinitely many fibers. So I think these are the first examples of say surfaces for which we can prove such a statement which are not embeddable in abelian varieties, for example. So I mean, most cases of proofs of non-Zariski density, Bombieri-Lang type results, they're done for subvarieties of abelian varieties, etc. These are simply connected surfaces. These are really very different examples of such things. Anyway, so this is curves, and I spend more time on curves than I was planning to. So let's go to the higher dimensional case. And then I'll go back to the Fano range, because then there's lots of interesting things to do there. So the higher dimensional case. So let xd be a smooth Campana orbifold over a number field k. And by smooth, I mean that the total space x, well, so that x should be smooth, and d should be a strict normal crossings. The support of d should be a strict normal crossings divisor on x. So d will again be of the form sum of the epsilon I di, where the epsilon I are taken from our favorite coefficient sets. Okay. And then the question is, what are Campana points on these higher dimensional pairs? Because well, what changes if you go from dimension 1 to dimension 2 is that the divisor d will now have a singular locus in general, and it's not completely clear how to define Campana points. I mean, and in particular the behavior with respect to the singularities of the boundary. So there's two notions. So again, I take some set of primes such that my pair has good reduction outside of the set, so that I can find a smooth proper model for my pair over OKS. So there's two notions. So definition. So say, for example, think of say x is the affine plane, and d is supported on the coordinate axis, for example, right? And say you have a point which lies at the a rational point which doesn't lie on one of these components of the boundary, but which reduces to the boundary modulo some prime p. Right? So I have a point which, when I specialize mod p, which will hit the boundary. So if my point reduces to a single component of the boundary, then it's pretty clear what the condition should be. Then you should just have the same condition on the intersection multiplicities as before, right? So you should require that the point intersects this component with multiplicity at least mi. But if my point reduces to, say, several components at a time, which may very well happen, then what do? So there's a choice to make. So a point P, a k point of my pair is a weak Campana point. Say OKS points on the model if the following holds. So if I take a place V not contained in S, and if the extension, so P extends to an OKS point curly P on X. So if P intersects the support of D, then I want the following inequality to hold. I want that the intersection number of curly D and curly P is not larger. So this is just the sum of the epsilon I times the intersection number with individual components. So I want that this intersection number is not larger than the sum of the individual intersection numbers minus 1. This seems like a weird condition, but it's for example, this says that if you are working with the affine plane and you have the two coordinate axes and you assign multiplicities 2 to each of them, then say a point like PP, which is not Campana with respect to individual components, but which reduces to the origin, that it is still a Campana point with respect to this whole boundary divisor, because it satisfies this kind of numerical condition. So this is a condition which takes the whole boundary into account in one go. That's one candidate, and it's been proposed by Dan Abramovich, this type of definition, and it's been used recently in a paper by Abramovich and Verodi Alvarado. And then there's a more restrictive notion. So we say that P is a Campana point. So if you want, you can think of strong or non-weak, but I mean, we just call it a Campana point in upcoming work with, I'll say this in a minute. So we say that P is a Campana point if our conditions hold with respect to individual components of the boundary. So by this I mean the following. So if I take a place V not in S, and if I take, well, if I have a component with coefficient 1, then I'm still not allowed to intersect it with my point P. But if I take a component with some multiplicity, some coefficient smaller than 1, then I want that this multiplicity will be at least 1 over 1 minus epsilon I, which is the mi we've been considering. Okay, so this is a more restrictive notion. It imposes tangency conditions for points with respect to individual components of the boundary. And one can check that set of weak Campana points is a larger set. And so I'm interested in counting points of bounded height on Campana pairs in higher dimension. And for a while, so this is the subject of joint work with Marta Piropan, Sho Tanimoto, and Tony Verodi Alvarado. So we've been studying equivariant compactifications of vector groups over number fields. So and points of bounded height on these objects. So there's very deep and beautiful work by Chamberlois and Schinkel, which treats these questions in the classical cases of rational and integral points. And so we've been trying to see to what extent we could generalize their results to Campana points, so this intermediate class. And by lack of time, I'll just say that so the results generalize very nicely for so-called KLT pairs. So pairs CD, for which all coefficients of components at the boundary are strictly smaller than 1. Then we really get a very nice generalization, I think, of their work. So the results extend nicely. And also the tools they use, they extend quite nicely. If you throw in some logarithmic components, so if you throw in some components with coefficient 1, then things become a little bit more subtle. So this is, I think it's a natural problem to look at. There's been other work in this direction as well, which I also want to mention. So just to close the circle. So I've been telling you about the problem involving squareful triples and counting points of bounded height, so Campana points of bounded height on the curve, parameterizing these squareful triples, right? So there's also been some work on points of bounded height in this direction. So if you take x is Pn over Q, so with coordinates x naught, xn. And if you take d to be 1/2 times, so I take the union of all hyperplanes, and then I throw in an additional equation. So this is the vanishing locus of the sum of the coordinates. Okay, so if you look at this pair, then the solution, well, so the Campana points on this object, they correspond to n plus 1 tuples of integers, such that all xi are squareful, and also the sum of the xi is squareful. Okay. So in Van Valkenborg, some 10 years ago, studied points of bounded height on this object, and he proved that the number of points of bounded height on this object, height bounded by b, is roughly c times b to the power n over 2 plus some error term. Okay. And this is using very different methods than the harmonic analysis tools used by Chamberlois and Schinkel, so using the circle methods. And very recently, this has been generalized by Tim Browning by Browning and Yamagishi, in which they vary the coefficients they assign to different boundary components. So they no longer want squarefulness, they want different different powerfulness conditions for different coordinates. So they have a generalization in this direction but with some funny numerical assumptions on the what these MIs can be. And this again uses the circle method. So there's been some work, and then there's also work in progress on toric varieties by Marta Piropan and Amare Schindler. So it seems that the time is ripe to propose some kind of Manin type conjecture for Campana points on these pairs, orbifold pairs. The most naive version of Manin's conjecture for these pairs has been shown to fail by Tim Browning very recently. But then I think with Marta and Joe and Tony, we've understood that if you are allowed to take out thin sets, then a general conjecture still seems a reasonable thing to propose. So I mean, there's a lot of activity I think at the moment in this direction. So points of bounded height on Campana orbifolds, but then in higher dimension. So anyway, so it's the end was a bit quicker than I hoped, but I just hope that you like these objects and that you see the value. I mean, I haven't discussed fibrations with higher dimensional bases, but there are also applications in that direction, and yeah, maybe you'll get some new problems out of this talk. So thank you. Yeah.
Very much. Are there any questions? Yes.
So going back to the results of Browning and Nitage that you mentioned earlier, can you make similar statements unconditionally if you assume that the base points are not individually rational? I mean, of course, after an extension, it's all the same thing, but could you make
so which results, Browning and
Nitage? For example, with the sums of squareful and cubeful integers, you know, if you don't assume that the base points are individually rational, can you still say something?
Yeah, you can always think about, well, potential density.
But for potential density, it's all the same thing, but can you make statements just over the base?
You can, but then you have to, the description becomes a bit less pleasant, I think. It becomes a bit more, yeah, it's not so clear to me.
Okay.
Yeah.
Thanks.
Thank you. So, other questions? Yes.
There's
yeah. Okay, could you please press the
So how does this relate to stacks?
Yeah, okay. So that's a very good question. How does this relate to stacks? So say you have, for example, a Campana curve, and you have these say you have P1 with 3 points, 0, 1, infinity, and we've assigned these multiplicities 1 minus 1 over m0 and so on. You can do a root stack construction, so you can root P1 at these 3 points. So take an m0th root that's at 0 and an m1th root that's at 1 and so on. And then you get the stack lying over this P1 with, well, so the coarse moduli map will be on the board. And so then you have points coming from the stack lying over this object, and they map down to Campana points on this thing, but only a very special type of Campana points. So in Campana's definition, we have these inequalities. We want tangency orders to be at least some MIs. The points you see coming from this picture involving stacks are those for which you have divisibility. So if you take so here you have some stacky object. If you take a point on the stack and map it down to this P1, then you'll get points for which these tendency orders are actually multiples of the MIs. But then Campana just has these inequalities, and these matter because that's what the whole fibration point of view, what makes the whole fibration point of view work. So and so there's no good uniformizing object for these Campana points, as opposed to if you just impose divisibilities rather than inequalities, then you do have a good uniformizing object taken via this root stack construction. So there is a link, but it's a very different behavior. So I mean, these inequalities make life just very difficult. I mean, think about, I've explained this problem with squareful triples. If I would ask you to just count Pythagorean triples, because that's what you would see from the stacks picture, then life would be easy. But the squareful triples problem is very difficult. So you see that It's not such a small difference. Yeah.
Okay, thank you. So, any other questions? Okay, no. So then, thank you again.